Hello class and welcome to lesson 1.6. Before we get into our lesson, we're going to take a look at one of the assigned questions for last day's homework or last day's work was to use a graphing calculator to accurately draw the parent function and each transformation. So this is what we're going to be focusing on today, ladies and gentlemen, how to shift different parent functions. And we're going to start off with the parabola, which is a quadratic relation, because that's the one we're probably most familiar with. So let's take a look at A, ladies and gentlemen. In example A, notice I've got 4 different colors here. The black is always going to be my parent function in every case. Okay, and then the different colors are going to be the effect of A. So what we're trying to focus on here is what is A. Okay, and our key point in this case is going to be discussing what is the value of A. For example, for the parent function, A equals 1. Looking at the red, or y equals, f at x equals 3x squared, that's going to tell me that A equals 3. Notice what's happened is it's 3 times as stretched. So again, that's what we call a horizontal stretch by a factor of 3. Taking a look at our green graph in this first example, we notice that A equals 1/2. Okay, which means when you take a look at the step pattern, it's wider than the parent function. And then lastly, we deal with the last one where A equals -2. Just remember, A tells us 2 things in this case. Negative means that it reflects the x-axis, that's why you see it opening down, as well as 2 means the step pattern instead of 1, 3, 5 is going to be 2, 6, and 10. Okay, which means it's more narrow. It's being stretched by a factor of 2. All right, now we're going to apply that to our new graph for the second example, which is our square root function. Okay, and again, we're taking a look at A. A is in front. Okay, if we look at our parent function here, for the first one, A equals 1. Okay. Taking a look at our second one, A equals 3. Let's take a look what's happened, okay? From the parent function, which is in black, what's happened to our red graph? Well, actually, it's been, again, it's been, my fault, it's been vertically stretched, okay, by a factor of 3. Taking a look at G at x in the green, A in this case equals 1/2. What does that mean? It means it's been flattened like a pancake, so it's half the height of the parent function. All right, and lastly, looking at G at x, A equals -2. The negative part tells us it reflects the x-axis, and the 2 tells us that it's twice as stretched out in the vertical sense than the parent function. All right, moving down to the new one, which is called the reciprocal function. Again, we're going to take a look at A being the same value. So for the parent function, A equals 1. For our red graph, A equals 3. For our green graph, A equals 1/2. And for our blue graph, A equals -2. All right. So what we have to remember, ladies and gentlemen, is for each of these cases, the transformation takes place depending on how we do this, okay? Now, we can't apply the step pattern to a reciprocal. So what we have to do is look for a key point. And the key point, you guys want to maybe make a note here, folks, is what's happening when x equals 1. So let's just write that down. Key point, x equals 1. What's happening to y? Okay, that should give you an indication. If I back up and take a look here at our quadratic, for example, and I compare the parent function when x is 1, y is 1, and then I look at the red graph when x is 1, y is 3. That tells you it's been stretched 3 times. When I look over here at my square root function, ladies and gentlemen, when x is 1 for my parent function, y is 1. If I compare it to the red graph, when x is 1 in this case, y is 3. That means it's being stretched 3 times. So the key point when you're looking at this type of graphs is what is happening to y when x equals 0. And that will definitely tell you the a value, or in this case, what we call the vertical stretch factor or compression factor. Okay, and again, we're going to get more into this when we do our notes. So looking here, ladies and gentlemen, at the reciprocal one, our parent function when x is 1, y is 1. When we look at the red graph right here, when x is 1, y is 3. That tells us it's been stretched 3 times in the vertical direction. All right. And the last one, our absolute value function. Taking a look, again, we've got our parent function. So in that case, a equals 1. Our red graph, ladies and gentlemen, a equals 3, and you will notice by looking at the graph, it's been vertically stretched 3 times. We could look at that key point. Instead of it being 1, 1, it's 1 and 3. Okay, that allows us to find the a factor if we don't have the equation given. And lastly, in the green, ladies and gentlemen, a equals 1/2. So when we have x equals 1, you'll see that the y is at the value of 1/2. All right, so that's a good understanding of using technology to help you explore this A pattern, or what the effect of A is on transformations. In the past, ladies and gentlemen, we've just dealt with quadratics, but now we're going to be dealing with transformations from all different types of parent functions. If you need to take a moment, come into class, grab a graphing calculator and ask me to help you with this, I will gladly do that. Or you can use the graphing calculator attached to my website. But please, if you need some help, come and see me. All right, let's get on with today's lesson. Transformation of parent function. Ladies and gentlemen, this is something you will need to develop. We will do this in most of our units. There are even other functions that we haven't discussed yet that'll come by later on. We deal with exponential functions as well as sinusoidals, and we'll be doing transformations to them as well. The important thing I want to start off with is back from grade 10, we used P and Q as our vertex. The thing with P and Q, ladies and gentlemen, is it only applies to the quadratic. So we are going to actually change P and Q to what we call D and C. And that is allowing us to do transformations to all parent functions. So we're going to learn some new letters today, okay, in terms of transformations. Okay, the A will stay the same, and you'll see where D and C will fit in a minute. All right, so let's take a look. Considering the following, ladies and gentlemen, if we have y equals f at x, that just tells us we have a parent function. Okay, then we apply a to it. Now a can do a couple things. Remember, a deals with your vertical stretch or compression. Okay, and if a is greater than 1, it's going to be a stretch, and if it's less than 1, it's going to be a compression. It's going to flatten it. But a also does another thing, ladies and gentlemen. It will reflect the x-axis, and that's only if it's negative. So imagine taking a parent function, very simple, then applying a, which tells us we're going to take that shape and either stretch it, compress it vertically, or reflect it if it's negative. And then we're going to add the d part to it, okay? So that's your horizontal translation. So when you add in the d, which was the P from before in grade 10, ladies and gentlemen, okay? So horizontal translation. Okay, so that's going to be left-right movement. Okay, and after we apply that, we are then going to deal with the letter at the end, which is C, and that's called your vertical translation. There's a spot on my board, ladies and gentlemen, that makes that go crooked. That's just not me being slanted. Okay? And when you do vertical translation, that's your up-down movement. Okay? So up or down. All right. And just remember, ladies and gentlemen, that the DC is the new kind of vertex that we talked about before, PQ. So just remember, PQ is the same as DC. We're just going to apply the DC to every parent function. For example, absolute value, reciprocal. They don't happen to have a vertex point, right? So that's why we're going to develop the DC, okay, as our vertex. All right. So what we have is a new formula. And this new formula, which is in the box here, tells us that for every parent function, we can perform any transformation. And this is something you can't graph this right away. And the reason you can't graph this in this formula is because I haven't told you what parent function to apply it to. So basically we can talk about the A, which is your vertical stretch or compression or reflection, your horizontal or vertical translation. We can do that to any parent function. So that's what that does. It describes a series of transformations. We just have to tell you, hey, what do we apply it to? How can you tell you can't graph this? Look, there's f at x in the middle. So f at x, that represents any parent function. It'll be easier once I show you how we apply this to different parent functions, okay? So let's take a look. For the first example, let's specify that, hey, let's apply some transformations to the quadratic, okay? Because that's f at x equals x squared. So what do we know first of all? If we apply a to it, it's going to be ax squared, because your parent function is x squared, right? Then we're going to apply the d. So what is that going to look like? X minus d squared. And then we're going to add the c. And depends on what parent function you have to make the order look different. That you should recognize, ladies and gentlemen, it's very close to your old quadratic. So if I write down below y equals a, x minus p squared plus q, you should recognize that that's in vertex form. Okay? But we're just going to be dealing with d's and c's instead of p's and q's. All right? Because p's and q's are very specific to just the quadratic. Now we're going to deal with another example. We're going to change up the parent function. So now we're going to apply a, d, and c to the square root function. Okay? So it's going to be a times the square root. Okay? And then remember to subtract d. D is attached to the x. So it's going to be x minus d all under the square root. And then to add c, c is by itself. So the third one is going to be x minus d and then plus c. Okay, so we're applying the a, d, and c to various parent functions that we learned last class. All right, next one. Let's take a look at the reciprocal parent function. So starting with that, what we're going to take a look at is a times 1 over x. This is one where it actually looks funny because the a, instead of being out front, is actually going to be on top because a times 1 is 1 for the numerator over the over x. Okay? So when I go to add the d, remember the x is always attached to the d part, or the d is always attached to the x, so this is going to be a over x minus d. And then to add c, it's going to be a over x minus d and add c. These, ladies and gentlemen, once we've got these final values in here, these are the ones we can graph, okay? These are the ones we can graph because we have specified what the parent function is. Sorry, live video here. Let me see if I can fix my spelling up there. These you can graph, okay? Just remember, if I go back up here, we can't graph it because I haven't specified which parent function to apply the transformations to. All right? Let's try one last one and then we'll do some other stuff here. Let's do the absolute value. Okay, so we're doing the absolute value function. A goes out front. Okay, then we apply the d, which is subtracted from the x, and then we add the, oopsie, sorry, and we add the c at the end. All right. All right, let's try this example. And again, sorry, back up the truck a bit for a second. This is something you could graph. Y equals, once those values were in, i.e. what if we replace that with the a, d, and c with different values, we could graph that transformation. All right? So, example 1, consider the transformed function of this value. And I apologize, I'll just fix that so you can read it. Okay. So what do we know from here, ladies and gentlemen? Well, based on this, we're not told what the parent function is because it's got f of x in it. But I can identify what transformations were applied. So, first of all, a is what value, ladies and gentlemen? It's -3. What does that tell us? First of all, it's negative, so therefore we know it reflects the x-axis. Okay, and the 3 tells us, ladies and gentlemen, we have a vertical stretch by a factor of 3. Okay, that's A. Now let's take a look at our D. D is 2. Just remember, it's x minus D, so the negative part stays the same. It's basically the opposite of what you see inside the bracket. Okay, what does that tell us, ladies and gentlemen? That tells us we've got a horizontal translation. And because the value is 2, it's going to be right 2. And the last one we can deal with, ladies and gentlemen, is the C. Okay, the C, in this case, equals 1. So that tells us we have a vertical translation up 1. So what does that mean, ladies and gentlemen? We can take these transformations that we just described and apply these ones right here, and we can apply it to any parent function. Okay? It just doesn't, we haven't specified which parent function we're taking a look at. In the second part here, in part B, write the equations for g of x if it's defined by. This is where we talk about the parent functions. Okay? Then we can graph it once we know which parent functions we're dealing with. So for the first one, g of x here will be, okay, if we're doing quadratic, ladies and gentlemen, the a goes out front, right? X minus d squared plus c, which is 1. Okay, with the square root function, if we were using square root as our parent function, g of x is going to equal -3. And basically what changes is the x portion. So it's going to be x minus 2 plus 1. Okay. G at x, when you take a look at the third one for absolute value, remember, a goes on top. Then it's going to be x minus 2 on the denominator, and then add 1. C is usually the easiest one to add, ladies and gentlemen. And your last one, oopsie, g at x equals -3, which is your a out front, x minus 2 in the absolute values, plus 1. All right, let's flip to the next page. Okay. For each function, state the parent function and the transformations required. Okay. Well, first of all, hopefully you recognize in this, in part A, the g at x, that our parent function, which is f at x, is really x squared. So that means it's a quadratic. Okay, and then it says to state the parent function, that's what we just did, and the transformations required. So all you do is say, hey, what's my a, d, c value? So in this case, a equals 3. What does that tell us? That we have a vertical stretch by a factor of 3. Okay, and we also know that c equals 2, and that's a vertical translation and if it's positive 2, that means we're going up 2. All right. Looking at example B, ladies and gentlemen, you see a fraction, so hopefully you notice that your parent function in this case is going to be the reciprocal because the x is on the bottom, right? So you know your parent function is that. Okay? Based on the parent function, basically, what has happened from here to get to here, i.e., what are my a, d, and c values, and then you explain. So for example, A equals -2. That tells us two things. One, it reflects the x-axis. Okay, and it tells us that we've got a vertical stretch by a factor of 2. Okay, it's A. Now remember, D, ladies and gentlemen, is right beside X. Okay, and it's normally it's X minus D. Well, how did we get a plus sign here? That means that the D must have had to be negative. So D is -1 because a negative times a negative gives you the positive. All right, so we have for here, ladies and gentlemen, a horizontal translation. And that, what does that mean we're doing? We're going left 1 because it's negative. And the last thing we need to take a look at here, folks, is your C. C equals -3. So that tells us we have a vertical translation. Vertical translation down 3. I just want to point out, ladies and gentlemen, if I could just back up for a second, I forgot to mention this. In example A, notice, ladies and gentlemen, that D equals 0. Okay, so what does that mean? That means that there's no horizontal shift left or right. You don't need to spot it. You don't need to tell me it. If you want to just write that down, that's fine. You could just write down no change, just so that you know. But it's not required because it's not a transformation because nothing's happening in that translation. All right. All right. Last question. Let's see if we can do it here. All right, so hopefully you recognize the absolute value signs, guys. You know that f at x equals absolute value of x. That's our absolute value function. Okay, a in this case, folks, is 1/2. What does that tell us? That tells us we have a vertical, and not a stretch this time, but a compression, because it's less than 1 by a factor of 1/2. Okay. D, ladies and gentlemen, in this case is 5. So that tells us we have a horizontal translation right 5. Okay, and lastly, we have C equals 3. And what does that tell us? That's a bad looking arrow. I'll just fix the arrow up here. Okay, so that tells us we have a vertical translation up 3. Just remember, ladies and gentlemen, I'm just going to summarize before we end up here. So we've got our formula, and it's g at x equals a f x minus d plus c. Just remember that a is usually out front except for the absolute value sign where it's up top. X is minus d and plus c is always at the end. Now, ladies and gentlemen, I will provide this formula for you on your unit test. I just want to let you know that we're going to add another letter to this, and we're going to add the letter K. So it's going to appear later on. So this isn't going to be your finalized formula. You will find a K added onto this in later lessons. Okay? So this is our transformation formula that we can apply to any parent transformation. As long as we specify what parent function we are using, that would eliminate the f at x, the f in that in the transformation formula, and then we could graph or analyze any function based on the transformations. All right, ladies and gentlemen, today's homework is based on a handout, which is called Transformation of Parent Functions. And you should get it in class. I don't see it attached here, but it should be on the website. All right. Have a great day, ladies and gentlemen, and see me if you need any help. I'd like you to master the A, C, and D before I add in another letter K. So please make sure you come see me for help, and we'll see you later.